today's speaker, Dr. Zhiyong Lu. Dr. Lu is a tenured senior investigator at NLM, and he leads world-renowned research in biomedical text and imaging processing, information retrieval, and AI and machine learning. And in his role as the Deputy Director for Literature Search at NCBI, Dr. Lu oversees the overall R&D effort to improve the literature search and information access in resources such as PubMed and LitCovid. And as you may know, PubMed is like the whole world's entry to the clinical evidence. And during the pandemic, LitCovid also served many people for retrieving, extracting the current evidence for COVID. And then it's used by millions worldwide every day. And additionally, Dr. Lu is an adjunct professor of computer science at UIUC. And then he has published 400 peer-reviewed publications. And it's a very highly cited author and an elected fellow of American College of Medical Informatics, ACME, and an International Academy of Health Sciences Informatics. So let's welcome Dr. Lu. And
thank you so much for the kind invitation. It's really a great honor to be here to share with you all some of the work we've done in recent years. So as introduced, I am part of the NIH intramural research program, and now we are part of the newly established Division of Intramural Research at the National Library of Medicine. So where I supervise a group of about 15 people, including trainees, doing researching AI and machine learning for both biomedical text and image processing. So the kind of data we deal with on a daily basis, including text data, that includes millions of scientific articles in PubMed and PubMed Central. When access is given, we also work on patient data, including electronic medical records, as well as patient image data, in particular in the fields of ophthalmology and radiology, because we have a great clinical collaborators at the NIH campus. So using AI and machine learning, we work on a wider range of different problems. In general, these are three areas. One is improving information access for the biomedical literature. As introduced, this is very tied to the mission of the National Library of Medicine and NIH. But beyond that, we are also interested in, from a research perspective, interested in extracting information from unstructured text and turning that into structured knowledge. Last but not least, using AI and these days large language models in healthcare applications. So for the next hour, I'm going to try to touch base on some of the studies in one of those three areas. But I will start with PubMed because this is probably something that everybody is very familiar with. In fact, you're probably the contributor of PubMed. Everybody, you have papers in PubMed and you are using PubMed in your own research. As of now, we have over 36 million articles, and every year that grows by more than 1 million. Every minute that grows by a couple articles. And on an average day, we have about 2.5 million users doing 3 million page searches and 9 million page views. That compares nothing to Google, but does make PubMed one of the top most used government websites by the federal government. So, and it operates 24/7 and 365, even when government shuts down. Occasionally that happens, but PubMed never shuts down. So even though AI and machine learning is a hot topic these days, but since day one, I've been at NCBI and NLM, we've always thinking about how we can using AI and machine learning to improve PubMed searches for our users. So here is just a list of search assistants that are made exclusively by using AI and machine learning. Of course, at the time, there's no large language model or even deep learning. So a lot of these was enabled by traditional or conventional AI and machine learning. But what separates us from Google or any other commercial or other search engine is that we try to be very transparent to our users. So for every search assistants, for example, we have either a scientific publication or at least a white paper, technical document, trying to explain to our users how AI was used to make this happen. And in fact, we also wrote a sort of a perspective paper using layman language to explain these features, as well as how our user responded to these computational features, because these features are widely used. But as much as I love PubMed, in the end, it is still a keyword-based search system. That means it does not really understand the query. To the opposite, it finds papers based on matching of the words in the query and the words in the document. So at the time, for example, a couple of years ago during the pandemic, a pressing need was to find papers, and only the papers related to COVID-19. Okay, and that became a hard task actually, because guess what? The word COVID-19 was not coined or used consistently in the literature until summer 2020. So all the papers published before that, which arguably is the most critical time for the research community and the wide general public to understand this new virus, were written all using a wide variety of different ways. So that was basically the motivation that we created a central repository called LitCovid. I always joke that this is a two and a half man project, because it was taken basically by two of my former postdocs and a little bit of my own time as well. So the whole purpose is we want to index papers, and only the papers related to COVID-19. And we started with manual curation, and then we actually made a great effort of integrating AI into this process, because as you can see in the next slide, manpower very quickly outpaced by the rapid growth of the scientific literature about COVID-19. We started with dozens of hundreds of papers, and then in the end we have 250,000 or even more. I think maybe 500,000 papers. But during that 4 years during the pandemic, we really served well to the scientific community. As you can see, it has been used over 60 million hits from almost everywhere, I think everywhere in the world, including people living in Antarctica. And this also turns out to be a great education project. A couple of years ago, we had a high school summer intern and did a project with us directly, and also this is her presenting at the AMIA high school symposium later on that year. So all I'm talking about so far in the first 5 minutes is just give you a sense the kind of work we did by supporting search. But these days, the problem is not you don't have papers, you can't find papers. I would argue it's probably the opposite. You have too many papers, because given a 3 or 4 keywords into PubMed or any search engine, you're returned with hundreds, thousands, tens of thousands of papers. Okay, so it's challenging for individual researchers like ourselves to read all these papers. We just can't afford the time to do that. So the million-dollar question is, can we have computers to read all these papers? Can we teach computers to read it and understand it just like human scientists, so that we can really leverage its power to scan thousands or tens of thousands of papers that humans were never able to do, but have the hope that they can make the connections or hidden connections in those papers to drive discovery. And so towards that goal, we made some baby steps. We tried to teach computers to understand what is a gene in the paper, what is a disease name in the paper. And the reason we're highlighting those entities, because we know these are most searched or thought concepts. So everybody, when you do a search in PubMed, we have search logs, so we know what people are searching in PubMed. So we find one of the very first projects when joining NLM is to looking for what are the topics people search. And you'll see here is that gene, disease, drugs and chemicals are indeed the fundamental and most searched topics. And that's where we focus on these topics first. You'll also be a little bit surprising to me. So these are not surprising in the red box, but a little bit surprising to me also is that 1/3 of the queries in PubMed contain author name. Now, but thinking back, it's not that surprising as well. We like to search for experts, people in this room, for example, or in this department. So thanks to two very hardworking and talented scientists in my group, over the years we have built a number of different taggers for recognizing disease names, mutations, genes and proteins, species, and chemical and drugs in free text. And as you can see, a lot of these tools has gone through over generations. Some of the tools has been gone for multiple rounds, iterations. And these were all built before the era of large language models. So naturally, people would ask, can you just throw these papers now to ChatGPT and ask ChatGPT what is a gene name in this paper? And guess what? We did that study, and there's a paper forthcoming. And what I can tell you is these fully supervised methods are still outperforming generative AI at this stage. Okay, and for those of you who are not familiar with this type of a text analysis, I just want to show you very clear what our tool, a tagger, is able to do. So given a bland or raw abstract, given this is a tagger for a sequence mutation or variant, we can tag in there are 3 occurrences of mutation mentions, and all 3 of them are actually referring to the same mutation. And with the gene information on the side, we can further normalize or map that, standardize this mutation into a standardized ontology or a controlled vocabulary ID. And in this case, we used RSID, which is the mutation database from the DB-SNP at NCBI. So we make all these taggers free and available because we are really a believer of open science. So what we found is that a lot of the teams or research groups would download these tools, and then guess what? The next step they do is apply these taggers to millions of PubMed articles because they want to do the process of finding the names in a large-scale analysis. So we thought, okay, why don't we do this for our users? Because for one, they're sort of repeating their work. For two, there are groups outside, they may not have the resources or the expertise to run these tools computationally, but they may be able to write a short API to retrieve the annotations. So that was basically when we created a project called a PubTater now more than 10 years ago. Essentially apply these taggers to all the articles in PubMed, 30+ million articles, and then aggregate its annotations in the back end and then render the results in the front end. So as long as you have access to internet and web browser, you'll see the computer annotations. And here is an example, because seeing is really believing, because now the tools, if we noted in the previous slide, are 100% accurate. Now, people can argue if it's not 100% that there are errors, are they useful? Well, guess what? Number one, humans are not perfect. If we ask 2 humans to annotate same gene names, I guarantee you they'll have different opinions. And number two, these quality of annotations actually do make a lot of uses in downstream annotations, downstream tasks. So we make this available you can access through a web browser. You can also access through APIs. And over the years, we have now over 1 billion API requests from many, many institutions. I'm pretty sure there are probably users at Columbia as well. Because of that user demand, especially used by a lot of the biomedical important biology databases in biology, because they use this to speed up their human curation process. So we made continuous efforts trying to improve PubTater. As I mentioned, we started more than 10 years ago, and in 2015, 2016, we added additional ways you can access the data through APIs or through FTP. And then one big improvement was in 2018, we decided to not only just text the abstract, but also text mine the full text. And that itself has increased content by multiple fold. And in 2019, as you know, the BERT model or the transformer model was introduced. So we used those more advanced machine learning to improve the accuracy of annotation. And last year or early this year, we launched the 3rd version of PubTater, where we added for the first time the biomedical relations. So we're not only annotating genes and diseases, but also annotating is this gene causing the disease, or is this drug treating the disease, or is this drug as a side effect or causing a disease? And not that we don't know that relation is important, but I was reluctant to adding relation into the PubTator because prior to last year, the performance was, between 50-60%. I don't think that's any good for the scientific community. But only when we had a data set prepared for the biomedical relation extraction and the relationship moved to around 70-80%, I feel that now is the time we really can add that. And even we add that, we're only adding that for the abstract only, because once you go into the full text, it could be much more noisy and the performance can drop quickly. So here is what the new PubTator is able to offer these days. You can look at this example where you have a disease name, gene name, and the variant. We text mine all these entities clearly, and then we normalize it to standard nomenclature, and then we put their relationship into a structured way. And PubTator is really versatile, but as I mentioned, it only text mine abstract and full text. But at the same time, we have a lot of users, and they have repeatedly asking us, begging us, you got to do some work with supplementary materials. And I was just like my attitude towards the relation, I was reluctant because guess what data people put in supplementary materials can be images, can be tables, can be PDFs, can be spreadsheet, all kinds of, I won't say junk, but all kinds of files they can put into supplementary materials. But eventually we did one thing. So we created a spin-off of PubTator. We call it LitVar. We only for one thing, we text mine variant annotations or sequence mutations in the supplementary materials, because this turns out to be our users are correct, because this is something that highly enriched only in the supplementary materials. All these papers, they may talking about 1 or 2 mutations in the abstract or full text, but a lot of the detailed data are only in the supplementary materials. So that's what we did, and we called it LitVar. Again, has gone through multiple iterations. So what LitVar can offer is you can search for a particular mutation, but you can also do a free text search. So you can search for a relationship between the mutation and the disease, for example. And this turns out to be very useful by those genetic counseling labs. They're trying to understand when they do a sequencing or they can genetic testing, and they trying to understand what are the mutations or what's the implications of these mutations to a particular disease. Okay, so this is our work with the scientific literature. And now I'm going to share gift a little bit, because I'll say that all the techniques or machine learning techniques I've worked with, in the last 20 years, starting from a heuristic rule-based system to naive-based, to conditional random field, to support a vector machine, to CNRN, to transformer, BERT model, and then nothing understand the human language any better than ChatGPT. I have to say that because, and that's certainly true, and probably also reflected in this slide, where it only took 5 days for ChatGPT to grab 1 million user, compared to much longer for other online popular systems such as Netflix. Okay, so about February 2023, just 3 to 4 months after it was launched, because my work at LLM and my previous work related to PubMed search, one thing in my mind is when people just give up using PubMed, because using PubMed, you have to come up with a query, you have to do your search, you have to read the papers. But if you just ask ChatGPT, it can answer your question directly, right? So that's when we started our pilot project, where we basically ask ChatGPT this question, because our previous work with COVID, we asked specific question related to COVID-19. So what are the most common symptoms of COVID-19, long COVID? And in this case, ChatGPT gave a list of 5, which is not that, to be honest, impressive, but ChatGPT seems to be extremely confident, because for each of the symptoms, it associates with a scientific evidence, literature, papers. But when we copy and paste those titles into Google or PubMed, we find nothing, because they do not exist at all. And these are completely fabricated, or everybody knows hallucination problem, right? Now, PMIDs are real, but these PMID have nothing to do with long COVID research. Okay, so this is certainly not something I would recommend to my colleagues. Say you can now using ChatGPT instead of PubMed. And at the time, also people have already talking about one of the ways to mitigating or improving hallucination is using retrieval augmented generation, a RAG system. Instead of asking ChatGPT directly answer questions, you can try to do some retrieval to giving you a question and then ask ChatGPT the same question. So we did that, but guess what? The retrieval system itself can be information loss because retrieval can return irrelevant papers, right? There's no guarantee your retriever will 100% give you the correct answers. So in order to avoid that, we say, okay, why don't we manually find papers that we know for sure are perfect related to long COVID research. Okay, and we identify those papers, and then we give those 5 papers to ChatGPT. Now, can you answer the same question based on these 5 papers? And this time, indeed, ChatGPT is able to answer the question much better. But if we highlighted there are still problems, basically, to the extent that I think that is our perspective paper last year, is that you have to do retrieve, you have to do summarization, but at the end, you still have this human expert verification if you think this is something for actual user. And now we did this as a perspective. We didn't really go beyond this simple example, but later I find in the literature, there are more concrete, detailed study like this one. They actually studied in a specific field of medicine, what are the statistics about hallucination. They find, for example, using nephrology as for literature search, you find about 31% of the reference were fabricated. So this gives additional evidence. I'll come back to say that even though we're now near the end of 2024, the problem still exists. We can't still blindly trust the results of ChatGPT for the same reason. But nonetheless, I'm really a believer because, like I mentioned, in the last 20 years of my research, I've never seen a tool is so powerful. And one example is its performance on those question answering tasks. And in this case, it's a task on the USMLE medical exam data, because this is the test that every medical student has to pass in their medical school, and a score of 60 is a passing score. And when ChatGPT 3.5, the very first version was launched, it already passed 60. Okay, and what's amazing is within 6 months, it achieved over 80% and very close to the human expert attending physicians. And I'm pretty sure now it's over that. Now people are so used to get these impressive results about ChatGPT, but I have to say, for people working in my field who have tried to actually beat 60 for many years, a lot of tools we have tried over and over the years, 1 or 2% considered groundbreaking prior to ChatGPT. So I really very appreciate the leap, the advance that this makes for the research community. But nonetheless, there are issues about using these multiple choice questions for performance evaluation, because one, in real world scenario, if you ask your physicians in this hospital, there's no ABCD to choose from, right? You give them a case vignettes or case patient information, you try to come up with your own diagnosis or treatment plan. So there's no choice to starting from. And number two, even the answer in the multiple choice may be correct, doesn't mean that ChatGPT actually understands the question very well. It could be random guessing, or could be better than random guessing, but there's no guarantee it's all correct. So that was basically our recent study called a hidden flaw. We found when we evaluated GPT-4V, and this is a collaboration also with Yifan from Cornell here. So when we did this was at the time, I think that was October last year when the the multimodal GPT-4V first launched. So the two questions we try to answer is, number one, is this multimodal GPT-4V model as good as human physicians when taking a question, both image and text altogether, okay, in a multi-question answering format? But more importantly, does the GPT-4 really making the decision based on a sound or reasonable rationale? And in terms of, does that understand what the image is about? Does it understand using the relevant using the relevant medical knowledge, trying to answer this question? And lastly, given given the information in the image and given the information recalled from the medical knowledge, does it make a step-by-step reasoning to make the eventually to get the correct answer? So in this study, we used the web version of the GPT-4V. We did a total of we started with 100 questions, but then we sent a paper for review, and then reviewers say this is not enough. So we doubled that size to eventually include over 200 questions. As you can see, this is coming from the NEJM online version, as the example I showed you. So this is example. Back then, you have a question, you have image, and then you have the answers. So these questions, we're making sure these questions were put on the online after the cutoff the date of the GPT-4V training date, because we're making sure these are not part of their training material for the model. And as you can see, these questions scatter across a wide variety of different domains, and that's why we have invited and recruited 10 physicians, including one medical student, because each physician would only answer questions in their domain, in their specialty. And then these questions were also scattered with different image modalities. Some are in MRI, some are CT, some are chest X-ray, and so on and so forth. So for the first question, it's actually quite obvious. Well, not obvious, but people are probably find this was probably nothing new, whereas the medical students basically gets about 60%, and physicians here is about 78%, and GPT-4 slightly over 80%, while there's no statistical difference. Now, I have to say, in this case, physicians, we specifically ask physicians to do this without any access to external resources. So they cannot say, I want to answer this question, but Google it first. You can't do that. Okay, but there is another version in the paper where they actually are allowed to using anything, external books, consulting a colleague, or do the Google search. And once they have that access in a sort of open book setting, their performance is actually way higher compared to the GPT-4V. I think they're close into the 90%. So this is the first part of the findings. And the second part, is perhaps the more interesting part, is the hidden flaws, as we call it, because we find that even in the 169 questions that GPT-4V answers perfectly, about 1/3 of the cases, there are some reasoning flaws, either in the area of, in different aspects, of course. The biggest category is image comprehension, so understand the medical image, followed by using the correct medical knowledge and the reasoning step. Okay, so that's quite alarming. And here is an example I want to show you that just showed you, especially on the right MRI image, where there's a clear abnormality in this for the eye, one of the eyes, but GPT-4V just didn't think there's an issue. I think there's a question. Oh yes. So how did we test the rationale? Great question. I left that detail. So going back to the study design, we first run GPT-4V on these tests, okay, these questions. And then the next step is, when we do that, we also ask GPT-4V to give your explanation in terms of those three aspects. And then for humans, physicians, we ask physicians to answer those, to pick the choices first. But then we also ask the physicians to look at, for each of the question in their domain, specialty, to make the judgment about these GPT generated rationales. So that's how we evaluate it. That's a great question. So so this is a clear example. So it's very, so in other words, humans will never make these mistakes. Even I'm not a medical trained personnel. I see this picture, I can say there's something different from the left eye and right eye. Okay, that GPT-4V would miss it, and this kind of, I would say, silly mistakes will actually making people not trusting the AI. Basically, you making those mistakes that human would never make, then you basically lose confidence by the potential users. And not just GPT-4 or AI large language have hidden flaws like that in the reasoning. We also find in 2 separate papers where they can exhibit bias because of their training data, as well as they can be easily manipulated and tricked by some adversarial attacks. A standard large language model would recommend a COVID-19 vaccine for everybody, okay? And that CDC also recommends. But you can easily make that trick large language model by adding an adversarial prompt or giving some poisoned training data. It will reverse that recommendation 100%. So it can be easily attacked. And that easy attack is very hard to detect, meaning that only for that particular task, it will reverse the answer. But in every other task, it is still performed just like a normal large language model. So that makes it extremely hard to detect if this is something that has been manipulated versus this is something that you can trust. Okay. Now, having said all of this sort of about negative aspects of large language model does not mean that I'm really negative about large language model. I'm actually a believer of this technique. Okay, so next, but I want to put these risks first before I actually talking to you one last project, which is we really taking advantage of large language model because of its powerful capability of understanding human language, and making something that I believe will make a big difference in healthcare, which is matching trials and clinical trials better. And certainly this is a real world needs from the NIH and beyond, because according to a previous study, about 25% to 40% of the cancer trials failed because of insufficient enrollment of a participant. And this is certainly something very important for our PIs at the clinical center at the NIH Intramural Research Program, because we have a hospital at NIH, that's Building 10, if you ever visit the NIH main campus. But it's not a normal hospital like yours here, because it exists primarily for supporting PIs running clinical trials. Basically, that's where the hospital is for. And the current process of finding the patients or having a patient referred from outside to our NIH trials is somewhat not very, I wouldn't say broken, even though that's the word from our physicians, but I think could be much more efficient. Okay, this process, it's done by professional nurses, but they are just out-resourced for the patients they have to connect with the trials. So our goal was trying to see using AI or using computational approaches to improve the efficiency as well as the equity in this process. Of course, this is not a new problem. A lot of people, including Dr. Wen, has worked on this problem in the past. There are different systems. I think the first paper is actually criteria to query is from Columbia, from Dr. Wen's group. But even though later on there are other also, that was published in JAMA, by the way, since Sue's here. And later on we have more advanced deep learning based models. But I will say these models, there are 2 limitations. I'll say one is for the deep learning model, they generally perform better, but they're performing better because they require massive training data. Okay, unless you have massive training data, you can build those models. Otherwise, it's not going to work very well. Number 2 is that it more or less serves as a black box. You have a patient, you have a trial, and then this model tells you yes or no answer. But guess what? We're not really trying to replace physicians or nurses for that matter. We're trying to building a tool that assists them, okay, make them more efficient. So we have to give them something, not a blind, a binary answer, yes or no, but also tell them why. And that's, if they can understand why, then there's a better chance they'll take it and use it. And so that was basically, I'll say, the novelty, the novel aspects of TrialGPT. And this was done by my current postdoc, Dr. Zhiyong in my group. So instead of taking a patient note and clinical trial and give a binary answer, we basically decompose that. We first look at each individual inclusion and exclusion criteria. And then based on that, scores on that each inclusion exclusion, we make TrialGPT or large language model to make some determinations. And then we aggregate the information from that criterion level to the trial level. So for each criterion level, we ask for three things. We're not just asking for, is this patient a good match for this criterion? But also, when we ask that, we ask, where's the evidence? Where's the evidence? Where's the relevant sentence? And if you have a relevant sentence, what information in that relevant sentence makes you think this patient should either be included or excluded? Okay, so here is an example where sentence A is one inclusion. It says traumatic injury to the head has occurred. So for this inclusion criteria, large language model or our TrialGPT would find that sentence 2 and sentence 3 are relevant because why? Because the patient hit her head on the corner. These are the information from those two sentences. And because that, then TrialGPT think this patient should be included for this criterion. So we do that for every inclusion and exclusion criterion. And by doing that, there are two main advantages. One is, as I mentioned, this makes this kind of explanation very transparent and useful for any potential user who would take this. Number two is that by asking explicitly the rationale or the reasoning, we actually, in a way, mitigate the hallucination problem. Okay, I'm not saying this can completely resolve it, but it significantly helped avoid some of the unnecessary hallucination. And the only way we know whether they do this, a machine does this correct or not, is through some evaluation. So we recruited 3 MDs. They annotated 1,000 patient criterion pairs. And they built this ground truth for us to compare. So when we did that, we find that large language model, TrialGPT in this case, achieves about 88 or 89% accuracy, which is very close, nearly identical to the human performance when we did that. And it's not perfect because there are still errors. And the error could be that large language model just does not have the medical knowledge. In this example, large language model does not know that angiogram can be interpreted as DSA in this case. There's another type of error where large language model just cannot make that connections. For example, the exclusion criteria is patients with multiple AVMs. And TrialGPT does not think there is multiple, there's not enough relevant information in the patient notes, even though patient notes mention this patient only had one AVM. Basically, it's not multiple, but ChatGPT doesn't make that connection. So it failed in this case. So once we have the criterion level evaluation or prediction, and then we aggregate everything into the trial level, and then when we compute 2 trial level scores. One is the relevance score, one is the eligibility score. So for a cancer patient, a cancer trial would definitely more relevant compared to a diabetes trial. But even just because it's a cancer trial does not mean this person is automatically relevant or should be put on the trial. So that's why we have the second eligibility score to determine whether this patient should be put on this trial or not. And using these two scores, then we can rank, for example, all the NIH sponsored trials in terms of their relevance. We can also immediately exclude the ones that we know they're not irrelevant. Okay, and that turns out to be a very useful thing, because often case is there's a lot of irrelevant trials, and without that information, a human nurse or human physician or trial coordinator, they would have to look one by one. But because we have a very high specificity, so we can basically save them nearly half of the time. Say, these are trials you don't even bother to look at. You can simply safely remove them. So because the work did by many others in the past, we actually have some public ground truth that we can use to benchmarking our methods. So thanks to people work on this through the track challenge in the past, there are 200 patients with 20,000 trials in total, and each of these pairs has been manually evaluated. So when we compare or assess the performance of TrialGPT, we can directly using these benchmarking data sets, because TrialGPT does not really utilize training data in a way. We do have some examples to teach TrialGPT, but not much. So as you can see, we achieve more than 80% of accuracy performance compared to the previous best is about 56%. And as I mentioned, on the criterion level, we are on par with human performance. And given that very encouraging results, we decided we want to study to see the impact, potential impact in regarding its utility. So we invited two clinical fellows at NCI. They did this study with or without the results of AI, and then perform the same level of trial matching, and we find we were able, using the results from TrialGPT, they were able to save 40% of their time with basically the same accuracy. There's no loss in accuracy at all. So this work has been under review for a while, and it's eventually will soon come out next month in November. And early this year, because of this very encouraging results, we're putting another grant. It's, as you will know, that as part of intramural research, we rarely have chance to submitting grants, which is a good bad thing, right? But we did for this case. There is a Director Challenge Award, so we teamed up with multiple PIs from the NIH Intramural Research Program, and we were fortunate to be selected for this prize, where we can, for the next 2 years, we're gonna study in different additional aspects, because we studied with oncology. That's where our initial collaboration comes from. But we want to actually building a prototype, and then also because we believe our method is really generalizable, because there's nothing says this can only working for cancer. So we're gonna working with other disease areas in the next 2 years, and we already built actually a prototype using the Microsoft Azure environment, because and this prototype, this chatbot, is actually available to all the NIH users, because this involves access to patient data. You don't want to operate this in a non-secure way. So Azure is HIPAA compliant, so we can actually safely letting our physician users to use this. Also, this requires authentication. So we have our NIH badge. So with your badge, we can allow you to log into this system. Now we are at Columbia. If anybody or everyone who's be interested in testing or working with us on this, we'd be happy to talking further. There is a way that we can make this also available to our external users. Of course, there's a cost associated, because every time you're using this system, we got billed by the usage of a large language model. But nonetheless, this is something that we are very passionate about. And just to wrap up, in the last 2 years, we've been really busy trying to working with large language model in medicine. And I always say there are two hands, both hands. One is the safety hand, one is the application hand. We trying to really leverage the power of large language model for doing a lot of things that may not be as good as ChatGPT, for example. And some example I just talked about. And because of that, this makes safety is really more important than ever before, because the AI makes it so close that we feel this is a time that AI can be deployed. So you really have to be ensure that the AI is operated in a safe, fair, and a secure way. Because without that, like I mentioned, like the hidden flaw paper, the trust can be easily lost in that process. And once you lost, you want to regain that trust, it's 10 times, 100 times harder. I can just guarantee you that that's just the human nature of doing things. So we need to making sure that before we making this in real world applications, these things are well taken care of. And that's sort of the both aspects of our research these days. We as a single research lab, I don't believe we can build something to compete with ChatGPT. That's not even part of the intramural. We have this debate. I don't know about Columbia, but we have this within NIH, whether there should be a domain specific coming from NIH or not. But I will say, again, this is my own, don't quote me on this publicly, but for a single research lab, I just don't think that's a feasible way of doing things. So instead, my approach has been, we trying to always augment enhancing standard large language models, because the things we can do now, if we build something from scratch and we finish that in 6 months or 12 months, guess what? The next generation of ChatGPT is coming out, and that's going to be even better than their previous version. So we are always, but the work that we are building is on top of standard large language model, so that regardless which version of large language model, we can always making that better. And we have the right to do this because there are domain knowledge, domain databases, domain vocabularies, ontologies that are not used. All these literature, PubMed, I would guess, are actually already used as part of training data by large language models. But I'm pretty sure the domain databases, like these databases hosted by NCBI or NIH or elsewhere, they're not actually human experts. They take a lot of efforts by human experts to curate in our domain, but are not used. And that's why I think that's the way to go. All right. With that, I mentioned some of the leads of different projects in my group. I'll be happy to take any questions you may have. Thank you very much.
And does anyone monitor the online question?
I'll keep an eye on it, but we can start with the room question regarding this.
Yes, can I answer 2 questions? Yeah, thanks to Dr. Lu for the great presentation. It's very comprehensive. And my first question is that you talk about the hallucination in the large language models, and you mentioned that in order to retrieve some kind of related papers, you manually get papers for the evidence, and you still need human experts for the verification. But I just wonder, if it will be low efficient to do that, and especially if you want to accept multiple requests at the same time. Can we build up a kind of reliable database which will include all the relevant papers, which can improve the efficiency for the search?
So it depends on the use cases, I would say. But if you're trying to using a RAG for answering clinical relevant questions, I don't think you can bypass the human verification step at this point, because even we're given truly relevant papers, as you can see, as the same as a question based on as ChatGPT based on those truly relevant papers, there still could be errors. So how can you blindly just trust whatever the ChatGPT is? And that's something that actually one of our active research projects is trying to building some, this is something we have talked about with Dr. One, is building some kind of scientific evidence. Once we have some kind of scientific evidence, then you're building a RAG on top of that can be more efficient. But I think if you're serious about using ChatGPT these days, you still want to do some human efforts.
Yeah, that's great. And also a follow-up question is that we talk about the TrialGPT.
Yes.
When you use the TrialGPT in the real life applications, you still need the human actor to verify the results of the TrialGPT. For example, if you say that the trial is irrelevant, you can still bypass it. You need the actor to verify.
Oh yeah. Like I say, everything we do, we're not saying that they should replace human nurses or human trial coordinators. So what we are testing right now is having, let's say, the TrialGPT can really be very versatile. It can take patient notes. It could actually take in just a brief sentences, an email from a referring physicians. And we are sort of doing a very initial screening process. Say, okay, because trial enrollment is actually quite complex process. We're trying to identify those eligible patients or eligible participants. By using TrialGPT, we can explain why this person should or should not be invited or not excluded. And during that process, we give reasons why. And that's why I was saying that these reasoning is really important. We give reasons why for each inclusion and exclusion criteria. And the person using the tool will actually make the final decisions. Still human physicians or nurses will make the final decisions. But even that, they basically is just doing the initial screening. They're still gonna have to invite the person in and testing for many other things before they eventually determine the eligibility. That's sort of a two-step process. Yes.
So I'm very interested in RAG on PubMed for my research, and I'm a big fan of PubMed in general. I was curious if you're working on sort of any standards or applications of RAG on PubMed that will, I guess, be a best-in-class source that researchers can go to. I know there are companies out there with open evidence and elicit.
Well, I wouldn't say we have research in that direction indeed, and I didn't go into details. So there are two papers here. One is the MediRAG paper was published early this year at ACL, and then we have a follow-up forthcoming paper at PSB 2025 in January. So you're already familiar with RAG, right? So there are multiple components in the RAG system. So at least you can choose what large language model you're going to use. You can choose what retriever you're going to use, and you can choose what corpus or the data you're going to retrieving from. Okay, and so all of this, as you can see, you can have multiple combinations of these different aspects. Okay, so in that MediRAG paper, we basically systematically studied which options, which combinations is optimal. So we come up with some suggestions. For example, if you have a general question, then PubMed is good. But you could supplement PubMed with additional textbooks, for example. And if you do that, performance is even better. Okay. So but differently, retrieving system actually does not make that big of a difference. You can use it as simple as, well, not as simple, but classic BM25 versus a more advanced semantic-based dense retriever, but the results are not that big of a different in terms of eventually ragging results. So that was the ACL paper. And then this new paper is that we find even in RAG, you can ask question multiple rounds. Just like when you're using with Google or PubMed, you don't just look at your search results and once and down. You actually sometimes modify your queries. Sometimes you actually change queries, or you sometimes using related queries. And that's the same thing with RAG. You can do multiple iterations. And that paper shows if you do that, it can actually further enhance the performance. So technically, that's, I would say, if I would use in RAG, that's one of the best practices I would recommend. So those two papers.
Awesome, thank you.
Yes.
Very general basic question, but you've done so much interesting research. I'm evaluating ChatGPT, and I see a lot of such projects coming up. I'm just wondering how generalizable is that kind of research if it's really focusing on ChatGPT and its performance, and also I don't know, I think you were mentioning something like that at the end of the presentation, that you could just run the same code from your research with the new model that they developed, and how can you use that knowledge for other generative AIs? And then maybe also, I'm not sure, aren't we, if everyone's doing research like that, are we kind of also helping ChatGPT to become the most relevant?
Oh, okay. So yeah, that's well, I think you have a valid point, which I should have mentioned it more clearly. So all these studies we've done, or in my presentation, I focus on ChatGPT, and for two reasons. One is that in our benchmarking experiment, it does seem to perform the best above all the other models we have tested, like Llama models, like Mistral models, like other domain-specific models. Okay, and that's, to me, that's still true in many of the evaluation papers we've done. We always actually choose at least one proprietary model like ChatGPT and one open source model. Okay, but ChatGPT in a number of evaluations do seem to have an edge over the other tools. Other tools are catching up. For example, Llama 3 70B models are catching up with ChatGPT 4 or 3.5, but then ChatGPT have 4.0, then ahead of making them, this is a very competitive space because, as you would know, a lot of stakes are very high, so they're trying to be very competitive with each other. So that's one of the reasons I mentioned ChatGPT more. And the other reason I mentioned ChatGPT more is for a lot of applications like TrialGPT, we extensively using that because we want to making sure we operate in a secure environment. And with ChatGPT and OpenAI and Microsoft have strategic partners, so they make this Azure very convenient for us to use, without having to, we have to build something. We want something that's most convenient and most powerful, and that turns out to be ChatGPT at this point. And that's why I mentioned that's more than any. But in our research papers, I'll say this way: we will never bypass a reviewer if we only do one model these days. They will always ask you for multiple models to compare.
Yeah, just follow up on that. Actually, I feel like the partnership between OpenAI and Microsoft is also dynamic. Just like the other day, I was reading news, like they started as very strong, and now they're thinking about kind of like going apart.
That could be. That's another thing. Is I think at NIH we have access to all three major cloud providers. We have access to Google, we have access to AWS and Azure. I think Azure was the first allowing us to process HIPAA compliant, give us a HIPAA compliant environment. But I think now AWS is also catching up. So with that, we will probably do that as well. Yeah, another question? Yeah.
Hi, thank you for this amazing overview of all of your work, a lot of your work. So a lot of my research is just concerned with promise and perils of AI for health equity. And in particular, I'm struck by some of the work you've done on unmasking and quantifying racial bias in LLMs, and even to some degree, I think adversarial attacks and risks are relevant. Characterizing, identifying, quantifying bias is a task that we do a lot.
Yeah.
Addressing the bias is much harder. So
Yes.
I'm wondering if you could talk a little bit more about your thoughts on how we fix the issue.
Yeah.
And perhaps some sort of judicious optimization of our RAG approach.
Yeah. I didn't. Perfect question. I didn't mention that much because this is something we're actually ongoing in my lab. I actually have a PhD student. At NIH we mostly have postdoc trainees, but I happen to have a PhD student from University of Maryland, College Park, very close to us, and he's in his fourth year, and his PhD thesis is about trustworthy AI. So, and all these two papers, couple of papers that we published here, including bias and quantifying bias and the fairness and adverse deterrent, he's the first author. And that's, like you say, quantifying, reporting that is probably not that, is something people do first, and that's what we did. And the current project is actually trying to mitigate or addressing these issues. So I can show you one, which is for the adverse attack, where I think it's a little bit harder to do the bias. There's one more easy way to do this, for example. And I had a discussion with him, which is, let's say, so in that We have a little bit of time. So how we quantify the bias? We basically take in real patient information, and then we artificially inject race information, white, Black, Asian, Hispanic. Nothing else has changed. And we would see that ChatGPT would give different answers when asking for treatment, when asking for diagnosis, stuff like that. Okay. Now, a simple way, naive way you can think about is when given patient information, you can ask ChatGPT to remove race information and then generate something. Okay, and in that way, it should be more balanced and universal. But that's not really fixed in the real problem because the model is still biased, and sometimes it's not always perfect or accurate to extract that race information, stuff like that. And sometimes you should really consider race as part of the treatment plan. So in the other study, adversarial, so we are now looking at the weights of these models, and we're trying to do something a little bit more sophisticated, because when we're looking at a TAP model versus a safe model, we see the weights are somewhat different. So we're trying to make some sense of this, changing some weights. Unfortunately, I can't go more in detail, but that's where we are looking at, is from fundamentally, can we change some weights and so that its behavior is safer?
We are just about at 2 o'clock. There's one more question on the Zoom for a couple minutes. But...
Sure, I'm fine.
Perfect. Fanny Chen asked, is there any way that we can easily transfer these annotation methods on clinical notes, such as extracting disease names or phenotypes from notes?
Yeah, great question. It's not, well, that's something exactly we talked about with Dr. Wen's group in the morning. I would say they are generalizable, but when you transfer to notes, sometimes, let's say disease, that's a perfect example, because we tried that actually on notes. Some of the tools actually worked very well on some of the EHR NLP challenges. But I would say, generally speaking, because our model was fully trained based on abstract, it tends to perform better on the abstract than on the notes. And there's just not a lot of publicly available EHR data available for us to work on that particular problem. At NIH, as I mentioned, we have a hospital, but that's not a regular, normal hospital, traditional hospital. So we don't have a very representative patient cohort that we can actually building something on. So I would say there is going to be some performance loss, honestly speaking, but it's probably still a very good starting point if you want to test it.